Great. Thanks to the organizers for the invitation. I'm going to take a slightly different approach to the talk today, and I'm going to come to it from an experimentalist point of view. And the idea of this talk is to give you a bird's eye view of where some of these open problems in cosmology stand and what the efforts on the ground are to go to the next level of measurements and sensitivity and what the improved limits we can expect in the coming years. So quick disclaimer, apologies if I missed your favorite experiment. I'm going to be biased towards the kind of experiments that I'm personally involved in. And if you find that any of my plots are not the latest constraints that you're aware of, then let me know, I will revise my slides. All right, so I'll be talking about three broad topics, namely experiments on inflation, focusing on detection of the B-mode polarization signal of the cosmic microwave background at degree angular scales. I'll also talk about cosmic dawn and epoch of reionization. And for this, the probe that we'll be using is the 21 centimeter signal from hydrogen, but I'll also be specifically talking about the global 21 centimeter signal experiments and where we're headed in that. And if time permits, I'll quickly touch upon a kind of a pet topic of mine, which is CMB spectral distortions, but we'll see if time allows for that. All right, great. So again, different version of this kind of same slide that everyone shows. We are here looking out into the universe, and the kind of three epochs I'll focus on are inflation, and the kind of signal that we will expect is something like this, which is the polarization of the cosmic microwave background, which has a curl component to it. Then I'll jump over a bit and come to this cosmic dawn and epoch of reionization, when the very first stars and galaxies formed, and what we can look from. And if time allows, I'll fill this gap here to go between kind of glossing over the epoch of recombination. So when we talk about, so when we talk about inflation, just to make this talk self-consistent and to kind of complete, what we're looking for specifically is when we make a measurement of the cosmic microwave background, typically at 150 gigahertz, and we clean out all the foregrounds, etc. We make measurements of the power spectrum of the CMB. And we have made excellent measurements that match very well, for the most part, with lambda CDM. And we have these TT, or temperature polarization, or the power spectrum, sorry. And we have now started making measurements of the polarization of the CMB at various scales. And we talk about two components of the polarization, namely the E and the B mode polarization. The B mode is believed to be the smoking gun of inflation. And specifically, this has a curl component, and it's observable at degree angular scales for the primordial B modes, which are seeded by the tensor perturbations during inflation. We've already started making measurements of the B mode at smaller scales, angular scales, or larger L, and this comes from lensing. But the dynamic range of the problem is really large, and what we're looking for is something way down here. And we parameterize this more broadly using R, which is the ratio of R, which is the ratio of the amplitude of the tensor to scalar perturbation. And there's a relation to the, depending upon the model of inflation, the value of the primordial tilt. So these are the Planck constraints, which have already started they started ruling out some maybe not so standard models of inflation. But I'll go back my previous slide. Beyond experiments, beyond Planck itself, there are several other dedicated experiments that have been trying to detect this signal from the B mode polarization. So these experiments are custom designed to look at this degree angular scale. And we've started getting some nice, interesting results, which are placing limits on the BB power spectrum. So from this, we jump forward to what I believe is the best current limit, which comes from BICEP 2021 release. And we've already started looking at a value of R of about 0.36, all right? Or this is the upper limit at 95% confidence. And this, of course, also takes into account previous measurements from Planck and BAO and so on. So where do we go from here is what I'm trying to answer. And for this, the challenge is that to improve the raw sensitivity of these experiments and to go to lower limits on R, to start with, we want to increase the number of detectors on these CMB experiments or CMB telescopes. We also want to improve foreground separation, so you increase the number of channels or the frequencies at which you observe the sky. You want to reduce or best calibrate atmospheric noise and instrument noise and so on. And you focus a lot on the map making strategy and how much of the sky you look at, etc. But the game changer, I believe, is going to be increasing the number of detectors in the CMB telescopes. So for context, we are currently in what we call as a stage 3 of CMB experiments. And these experiments have tens of thousands of detectors on their focal plane. And these are some of the experiments that I've listed here. And I work with Simon's Observatory. And the detector that we use are transition edge sensing bolometers, or TES bolometers, which are essentially superconductors that you have that you bias and are placed in the focal plane. So you have the optics in the front end, which does all the nice things of collimating the light, filtering it out, and passing it on to this detector. And what this detector essentially does is that if biased correctly, you have a change in the resistance of this superconductor when biased at the transition, when you have energy. So a change in temperature is reflected very easily as a change in resistance, and this is what you measure. The next generation, which we are all working on and the community is working on, is to go to the order of magnitude of hundreds of thousands of detectors. And one such experiment that's already in the works is CMB S4, and I'll come to that in a bit. So here is a quick overview of Simon's Observatory. The Simon's Observatory has 3, now maybe 4 small aperture telescopes. And these are the ones that are going to be focusing on detecting this degree scale polarization of the CMB. And in total, Simon's Observatory has 60,000 TS detectors. And here are some numbers, but the target level of R for Simon's Observatory is 0.01. And one of the ways we are going to get there is by having several of these detectors, like I mentioned, at the focal plane of the telescope. And one technology that is currently being adopted by Simon's Observatory is called microwave squid multiplexing, in which you have one detector which is associated with, say, a certain frequency in gigahertz regime. And if you have several such detectors, say if you have thousands of these detectors, each of these detectors is read out using a uniquely assigned tone, which is a different way of saying that I have found out a way to pack thousands of detectors in a small volume, but read the information out of these detectors using just one cable instead of hundreds of thousands of these cables. And that is going to be a game changer in terms of improving the raw sensitivity of the telescope. So this is another picture of what this might look like and what I just discussed. So I'm going to gloss over some of this because I know that the audience is quite diverse, but we can come back to some of these details during the discussion. So here is the constraints of the forecast from Simon's Observatory. So this is what I showed you. The gray stuff is what I showed you from the Planck results. And what the goal for Simon's Observatory is the red contours. These are the 68 and 95% contours. And this is the baseline. So the bare minimum, this is what we should be able to do, but this is what we would like to get to. Beyond Simon's Observatory, we also have other experiments, namely LightBird, which is an experiment that will be in space, led by Japan and the US and others. And this will target This will target an R of 0.003. And this, again, for context, Simon's observatory is here in gray, and this is what LIGHTBIRD will seek to do. So coming to the even more futuristic next generation, say complementary to LIGHTBIRD, but on the ground, is CMB S4 or CMB stage 4, which will have hundreds of thousands of these detectors spanning 21 telescopes between Chile as well as the South Pole. This will comprise 18 small aperture telescopes and 3 large aperture telescopes. Just for context, when I say small aperture telescopes, they have smaller apertures. So they're looking at slightly larger angular scales. So the degree scale polarization signal will be detected by that. And this is a forecast from CMB S4. Again, CMB S4 will try to target an R of 0.001. And here are some of the other current constraints and this kind of parameter space that you're delving into. So you're kind of starting to get into the more interesting but currently extremely accepted models of inflation with these kinds of experiments. All right, now I'm going to quickly change gears. Again, jumping over a bunch of topics, happy to talk more about it later. The other open problem in standard cosmology is we don't quite know when and how exactly the first stars and galaxies formed over this period known as cosmic dawn. But we do know that eventually the radiation from these sources re-ionized the neutral hydrogen. So we currently live in a mostly ionized universe. So kind of questions we don't know the answers to are exactly when this happened, what the nature of these first sources were, how, what kind of radiation they emit and how that interacted with the gas. There are multiple probes. Some of them are better suited than others based on the redshift. But for example, CMB can give us a constraint on the integrated optical depth to reionization. But that's not necessarily the best way to study reionization. There are other more interesting tools. You can look at the Lyman alpha forest. And a critical and an important tool is to look at the 21 centimeter signal from hydrogen. You can make measurements of this signal in various interesting ways. You can look at the average evolution of this 21 centimeter signal from hydrogen as a function of redshift. You can also make a power spectrum of this 21 centimeter signal. And eventually, in a futuristic sense, you can start making direct images of this signal. I'm going to focus on this global or monopole signal. Here is what an example of what the signal looks like, but let's pay attention to some of this shape here. So I'm going to go back and reintroduce you quickly. I know there are lectures on this later, but the 21 centimeter signal comes from the spin flip transition of the hydrogen atom. And essentially, it's characterized by what we call as the spin temperature or TS. And this TS is proportional to the number of atoms in the spin anti-aligned to the spin aligned states, all right? So what we're actually measuring is not TS, but the differential contrast of this TS against the radiation background. So what we're trying to measure is this quantity, where it is, like I mentioned, a differential contrast, but it's also a function of the actual amount of hydrogen present, the neutral hydrogen fraction. All right, so let's understand the shape of the signal we're trying to detect. In the very early redshifts, so what we call as the cosmic dark ages, even though photons and baryons have decoupled during recombination, there is still some residual coupling. And this causes the spin temperature and the CMB temperature and the gas temperature to all be equal. So more or less everything is the same. And there is adiabatic cooling, but eventually the expansion of the universe is large enough such that the collisional coupling, which is causing this to be equal, is no longer effective. So your spin temperature now starts tracing the CMB temperature. So there's not enough gas molecules or atoms for this to bounce off of. So it's mostly coupled to the CMB. So it drags this temperature back up. But then the first galaxies start to form. And then what you have is you have something called as the Wottyson field coupling, where you have Lyman alpha starting to play a key role in coupling the spin temperature to the gas temperature and brings it back down. Once you have X-ray heating from these, say, first sources, you start increasing this temperature back up and potentially increasing it above the gas temperature, or the CMB temperature. And finally, your neutral hydrogen fraction goes to 0. So because of this, your signal goes to 0. So that broadly describes the shape of this. And based on the astrophysics and cosmology that you're talking about, various things like the amplitude of the signal, the width of it, the actual position of it all start to change. So by making an accurate measurement of this shape or the signal as a function of frequency, you're able to understand astrophysical as well as cosmological parameters, and then understand this epoch of cosmic dawn and reionization. So this is a sample of some of the standard cosmological model predictions of, say, cosmic dawn. Dark age is not included here, cosmic dawn and reionization. And as you can see that the playing field is quite wide open. We don't quite know which signal is the real signal and what these parameters of CD and EOR are. But we've already started, sorry about the resolution of this, we've already started placing some constraints and started rejecting some of these models based on experiments on the ground. So here are some of the models that have been rejected. And just to summarize, what they have in common is inefficient X-ray heating and rapid reionization. So those kinds of models are starting to get ruled out. All right. So this is another kind of a current constraint, more on reionization, but not necessarily from global 21 centimeter signal, but more from Planck and Lyman alpha forest, which kind of brings us around the redshift of 8 for reionization. And on the y-axis is the neutral hydrogen fraction. So summarizing in words and not in a plot, what the current constraints from global 21 centimeter experiments are that we have more or less ruled out instantaneous or extremely rapid reionization, and this has been done a while ago now. We've also ruled out, like I mentioned, inefficient X-ray heating with rapid reionization, some of these models, and our sensitivity to some of these models come from the way we're also separating foregrounds. All right. And we've also started ruling out some exotic models, which was famously claimed by an anomalous detection by the EDGES experiment. There are more talks, I think, touching on potential explanations for that model, but at least the SARAS group that I'm a part of has kind of experimentally at 95% confidence ruled out the EDGES detection. All right. But I want to take you a little further to see what's going on next in the field in terms of experiments. While we have several experiments on the ground that are focused on detecting this global 21 centimeter signal, there is a lot of reasons to believe that if you go to space, and specifically if you go to space to the far side of the moon, that is an ideal environment to make a clean detection of this signal. So some of the reasons why we don't want to be on Earth are you have plenty of radio frequency interference. So for those who didn't catch the x-axis on some of my previous slides, the frequency range where we're expecting this signal goes somewhere between 40 to 200 megahertz. And you might recall that about 88 to 108 megahertz is where your FM frequency or FM radio frequency is. So you are kind of swamped with radio frequency interference on Earth. You also have potential effects of the ionosphere, which can cause a confusion in the signal detection. And there are other complications that come from just having an experiment on Earth and the way that sensitive experiment picks up things not only from the sky, but also from the Earth beneath it and its surroundings. So there's a good reason to believe that the far side of the moon is an extremely radio quiet and pristine place. This has come from experiments way back when in the 60s and 70s, but also from recent simulations using a more complex model of the gravity of the moon and so on. You understand that the lunar far side is extremely radio quiet and that it can attenuate RFI from the Earth. All right, so you have a nice quiet place to go do your experiment. And there are several such experiments lined up from across the world that are targeting to do this at different frequencies with different observing strategies. So not all of them specifically targeting EOR, but getting there and will help with things like foreground separation and so on. So several of these are landers. Far side is no longer active. I was going to mention there, I'll come to that. Sorry, far side, there's another experiment called Farview and Dapper. These are all from the US. This is Hongmeng from China. IISER has something in the works. And I'll specifically talk a bit more about Pratosh that I'm leading at the Ramanujan Research Institute right here. So I should mention here that there are two experiments called Lucy Knight and Rolls, which have already been approved by NASA, which will be operating at slightly lower frequencies, but they will be landers and they'll pave the way for some of these future experiments. Okay, so I'll talk a bit about Pratosh. Pratosh stands for probing reionization of the universe using signal from hydrogen. And Pratosh in its final vision will operate over 40 to 200 megahertz. But currently we're working on an experiment targeting the cosmic dawn over 55 to 110 megahertz. And instead of a lander, we've made a conscious choice that Pratosh will be a lunar orbiter, and it'll take measurements when on the far side of the moon, and it'll transmit data back down to Earth when on the near side. And we have proposed this to ISRO in 2018, along with other experiments like SEAMS and Daksha and so on in the same call. And after completing about 2 years in this pre-project study phase, we've been recommended by a technical review committee to be considered for project mode. And we are working towards getting to project mode. This is what Pratosh looks like in a simplistic toy model, where we have a very interesting looking custom designed antenna. And this sits right on top of the payload electronics as well as the spacecraft electronics. And we've started building this as a ground-based model, and I have pictures later which I can show you. And this is the kind of limits that we expect from Pratosh. So again, we're kind of more sensitive, of course, in terms of central frequency around 78 megahertz, where the cosmic dawn trough is the deepest and where the turnover points occur. And also we've kind of designed the experiment to be centered around this frequency because that's where we think most of the models lie. We have, in terms of amplitude, we can go down to about 200 millikelvin or so. All right, it looks like I do have time, so I'll quickly touch upon CMB spectral distortions that were mentioned by Rajiv in some context, but I'll quickly go over this. So when we think of the CMB, we think of CMB as this perfect black body. But let's look at the properties of a black body, right? So black body has a certain intensity, which is given by this, which we understand is determined by its temperature. But a black body also has other specific properties like its energy density, photon number, and distribution. So if I do something to inject some energy into this black body and just change its temperature, sure, you can get some kind of equation that looks like this, but it's not going to be a black body, all right? You're going to have, you need to redistribute the number of photons as well as the occupancy of those photons to retrace this curve. So in the early universe, we have some processes that help do this, namely double Compton scattering and Brent-Stellung, which can help change the photon number. And you have Compton scattering, which can change the energy of the photons. So until about a redshift of about 1 million, all these processes are reasonably effective. So any process that injects energy into the background radiation will rethermalize, and you get a black body back again. But beyond a certain point, there are other processes that's if they inject energy, for example, the formation of the atoms, which you expect will release recombination photons, they should be preserved in the CMB spectrum as a distortion to this black body spectrum, which has never been detected. But very much within the framework of lambda CDM, you do expect the CMB spectral distortion to exist, but they have never been detected. All right. Similarly, you also have distortions, for example, when this double Compton scattering starts becoming ineffective, you have mu distortion, and then eventually you have Y distortion, which is from the Compton scattering, and in between, you have this something called residual distortion, which is not necessarily a linear combination of mu and Y. Right? So the current best limits for these CMB spectral distortions come from FIRAs on COBE, which are like decades old now. And these are some of the values that we have limits on to about 1 part in 10 power 5. We believe the CMB spectrum is black body, which is expected even from theory. But from theory, you expect also that inevitably there will be distortions in the CMB spectrum at much lower levels. So there have been experiments that have been proposed, but none of them unfortunately are funded yet. But these are some of the kind of estimates that you would expect and the kinds of detections you will expect from some of these experiments, like pristine, pixie, super pixie, and so on. But what I'd like to point out here is that some of these signals, for example, cosmological recombination lines, which is something that's of interest to me, are also sensitive to certain cosmological parameters, including things like H naught or baryon density and so on. So any processes of energy injection or any exotic energy injection models that perturb the CMB spectrum beyond a redshift of 1 million, so less than a redshift of 1 million, will be something that will be picked up by CMB spectral distortions. And that is something that I think the community should start looking to, even though it can be quite futuristic. So I think I'm going to wrap up here. I got my warning, but I'm going to wrap up here, which is that tremendous progress has been made, and we are truly in the regime of precision cosmology. And I'm, as an experimentalist, I'm looking forward to these experiments coming off the ground, which will actually start putting very interesting and useful limits on some of these models of inflation. And we're also now heading in the direction of taking to some of these 21 centimeter experiments to space, which along with the ground-based experiments will start placing limits on cosmic dawn reionization. And CMB spectral distortions are definitely a futuristic frontier, but definitely I think once we start coming to questions that need an extra additional probe to kind of finally put the nail in the coffin, including things like Hubble tension, I would be personally interested to see which direction this takes in terms of experiments. So I'll stop there and take questions. Thanks. Yeah.
Thanks for that. So you said the CMB stage 4 is 10 to the minus 3.
Yes.
So let's, if I'm being super optimistic, what are the maximum limit probably possibly people are thinking? This R, a small number.
Oh.
I mean, is it the CMB stage 4 is something that's all that people are talking about, or something more?
That I know of, yes, S4 is there, is the lowest in terms of R as an actual experiment that's being taken seriously, yes. Yeah, but S4 and Lightbird are kind of complementary, but yeah, S4 from the ground, Lightbird is 0.003. Yeah.
So the concern is that this 0.1, 10 to the minus 2, 10 to the power minus 3, all remains in the same scale of inflation. Even if you're lower by 1, none of them are going to be sensitive. So that's
yes.
the only concern.
Yeah, I understand, but I think right now that at least I know of in the horizon, S4 is what I'm aware of. I know there are, for example, I don't know off the top of my head what the numbers are on those, but I know that CMB, HD and Bharat, etc. are being discussed, but I don't know exactly what their limits are. But S4 and Lightbird for sure are happening. So yeah.
So you mentioned this, was it Sarah's 3 or something?
Yes.
Excluding edges at some confidence level.
Yes.
Can you explain that a little bit more to me and give some more details?
Yeah, yes, I can. I'm not quite sure, but next week, I believe there might be a talk on that. I don't know, sort of. Yeah, but I can give you a quick summary. So basically, Saras 3, we brought the results out in 2020. So Saras 3 is let me see if I have pictures, but I have a lot of slides. Okay, I'll walk you through it. I can show you later. So Saras 3 is a ground-based experiment, which observed specifically targeting this signal observed by edges. So Saras 3 observed in radio quiet locations in India over 2019. And we had a custom designed radiometer floating on water. All right. And we found that we were able to exclude this extremely deep and wide absorption models, including the signal observed by edges. So we had sensitivity going below the, say, 500 millikelvin limit, which is where the edges signal was seen. Unfortunately, we didn't have sensitivity to go even lower and start ruling in the more standard models. But we found that about 95% confidence, we were in disagreement with the edges data. But there'll be a detailed talk on that next week. But I can show you some slides and walk you through some of the results in the break on the discussion.
Yeah, show me in the break.
For sure.
Thanks.
Yeah.
I'm not sure if I missed it, but when you're talking about constraints and reionization using the new Pratosh experiment and stuff that you guys have, did you also include, I think there are also some things like spherics and others coming, are they probing the same range that you're probing, or is it different parameter spaces? Can you talk
It will be probing reionization, but like this will be the 21 centimeter experiment that Pratosh is looking more for the cosmic dawn signal. So we are not right now targeting the reionization signal. We are specifically focusing on the signal of cosmic dawn in the first phase. Yeah. Sphere-X.
What is the redshift?
We are now centered around about a redshift of 18. Yeah, so we're going from 55 to 110 in megahertz. So basically we're centered around redshift 18. Not that much. Yeah, we're going little further. Yeah.
Thank you. Thank you for a very interesting talk. Can you say more about the pros and cons of a lander versus orbiter for these 21 centimeter moon experiment?
Yeah. So the landers have the advantage that they are not constantly going in and out of the sun. And that is a big advantage because one thing that you don't want to do is to start messing up your antennas and your experiment by just going through these large thermal fluctuations. But when they land on the moon, they're permanently in a relatively radio quiet location. And the way you get data out is you have another orbiter that picks up the data and brings it back to Earth. So they are in a permanently, like in a stable environment. That's a big advantage. However, they have the disadvantage that we also have on the ground on Earth, in that you are sitting in an environment that you don't understand very well. And it's really hard to model it to 1 part in a million that you need to do. Which again is the advantage of an orbiter, because you're literally in free space. And when you're observing, you're in pristine, like a radio quiet environment. But again, you have the disadvantage that you're going to keep getting hot and cold over multiple cycles. So it's a kind of a design decision about which of these two devils you want to deal with. So we from our experience on the ground have decided that it's a lot harder to model the ground to that many wavelengths deep on moon, which you don't know very well. You might as well do the thermal stuff that you think you can understand through modeling. Yeah.
Thank you. Very nice.
Yeah.
Okay, so let's thank Mayuri again for a nice survey talk.